from the Central Illinois NSBE Junior Chapter, and I'm going to be presenting finding absorptivity of colored water using a cell phone spectral photometer. So let's get started. So you guys remember this debate from about a month ago. It was the stupidest thing I've heard in my life. People were trying to decide whether or not the dress was white and gold or black and blue. It's black and blue, by the way. But we figured out why it was. It was because something weird with Photoshop and the way the picture was uploaded online. But I want to take this a step further. So how are colors created in clothes? Well, there's these fancy chemists in these fancy labs that combine chemicals together to make dyes. And those dyes are put into fabric and they make the clothes that we see. Let's take that a little bit further. How do those chemists know what dyes, what chemicals create those dyes? This goes directly into my project. So colors form by the absorption of white light into a medium. So white light is created by all of these colors. That's your blues, your pinks, your yellows, magentas, all of those colors. All of those colors vibrate at different frequencies. So if you want to make a red shirt, the red dye in that frequency, the red dye has to vibrate at the same frequency as certain colors inside the color spectrum. That dye has to absorb all of the colors except for the color red. So the colors that we see are the colors not absorbed into the medium. In analytical chemistry, there is a law called Beer's law that describes the relationship between absorptivity, concentration, and the path length of radiation. The law is A equals A times B times C. Big A being absorbent. So using the red shirt example again, this is how much white light is going into your shirt, period. Little a is absorptivity. That's how much white light is being absorbed into 1 centimeter of your dye. Path length of radiation is how long it takes that white light to get through all of your red shirt. And concentration is how much red dye is in 1 liter of water. So in my project, I wanted to use Beer's law in a real world example. See, we learn all these laws in school and stuff like that, but we never get to use them. So that was the whole purpose of my experiment. So in order to do that, I created a cell phone spectral photometer, which is a fancy way to say a thing that can analyze light in whatever medium that you have. So in this experiment, I have two hypotheses. The first hypothesis is that the wavelength at maximum absorbance will be on the opposite end of the spectrum that we see. So you see in this pie chart, you have green. If you want to get a red shirt, the maximum absorbance has to be somewhere in this green section. If you want a blue shirt, a maximum absorbance has to be somewhere in the orange section. Again, the colors that we see are the colors that are not absorbed. My second hypothesis is that the absorptivity of each sample will be the same. The reason why I believe that is because concentration is going to be kept the same for all of my experiments. Path length of radiation is going to be the same. I bought all my dyes from the same store. I figured absorptivity must be the same. So in order to build this, I need a cell phone. Most of this stuff I can get online. The diffraction grating was a little bit more expensive, but the water you can get at home, you know. All right, so this is what happens once I close the lid to my box and I take my pictures. You get these things right here. So this is the color of clear water, that's blue water, red, yellow, and green. Those were my 4 samples. This diagram right here shows exactly what's happening when I take that picture. So you have the light, and it's going through the cuvette and the sample. The sample is inside the cuvette, of course. You can't have water by itself. And then you have the diffraction grating, and then you have your camera. This is basically what's going on when I close that lid. So then I take my pictures from my camera and I upload it to a program created by the University of Illinois. I select my pictures, I make a little green line. That shows like where everything is, and then it creates this graph. So at the bottom of the graph, there's wavelength. So at each wavelength, there's a certain color. If you remember back at that color wheel I had before, around the 700, 600 range, that's where your reds are, and around 400 range, that's where your violets, and in the middle is where your yellows and your greens are. So these are my results once I did my red and my blue sample. If you notice, the blue sample, the color absorbed is around where the red is, and the color that we're supposed to see was green. The only reason why I believe that happened was because of just the way our eyes are. This is food dye, this isn't regular like clothing dye or regular science dye. So I think that just the way that my eyes see blue, it doesn't necessarily mean that that is the color that's presented. Same thing happened with yellow. Yellow, it absorbed, It absorbed around in the green spectrum, blue spectrum, and the color that we were supposed to see was supposed to be a reddish orangish color. Again, I think that's just the way our eyes work. If I were to create the dye, I don't have it with me right now, but if I were to create it, it looks yellow. So when I was looking at my results, the first thing I noticed was that the absorptivity of green was really high compared to the others. If we look back, green was like 0.24, while the other ones were less than 0.24, which is a lot. I started questioning my experiment quality. I was like, well, maybe I need to buy more dyes. Maybe I need to use a different box. Maybe I need to buy a better cell phone. So in order to answer those questions, I compared my original hypothesis to my data. And this is what I found out. So my first hypothesis was true for the most part. Again, red and yellow and blue weren't quite what they were supposed to be, but I think that was just my eyes playing tricks on me. The second part of my second hypothesis was not the same at all. Again, green had the greatest absorptivity by far. My first theory as to why this happened is that green, if you look on the ingredients on the box, it was yellow 5, yellow 6, red 1, blue 1, and red 40. As you can see, I didn't say green at all. That means that blue 1 and one of the yellows was used to create green. So I believe that because there was a greater variety of absorbing particles, there was more white light absorbed into the green sample. My second theory is that the company just used a higher concentration of green. Again, this is food dye. This is the same type of stuff you use in your green cupcakes, so that's probably why it was so much higher than the others. So thank you very much. These are my references. I want to thank Caterpillar for funding this trip, Central Illinois NSBE chapter for letting me come here. This is my first time and I'm extremely excited. Bradley University and Peoria High School.